Welcome to Physics Dream Team Classroom, Kolej Matrikulasi Pahang Kementerian Pendidikan Malaysia.
Chapter 9, Simple Harmonic Motion. For overview, this topic can be split into 4. We start with simple harmonic motion parameters, then we go to simple harmonic motion equation. From equation, we can sketch graph, and finally, we end with simple harmonic motion system. Simple harmonic motion is defined as a periodic motion without loss of energy in which the acceleration of a body is directly proportional to its displacement from the equilibrium position and is directed towards the equilibrium position but in opposite direction of the displacement, or mathematically, A equals to negative omega squared x equals to d squared x per dt squared, where A is acceleration of the body, omega is angular velocity, and x is displacement from the equilibrium position O. The angular frequency omega always constant, so A is directly proportional to negative x. The negative sign in the equation indicates that the direction of the acceleration A is always opposite to the direction of the displacement x. The equilibrium position is a position at which the body would come to rest if it were to lose all of its energy. Example of simple harmonic motion system are simple pendulum, horizontal, and vertical spring oscillations as shown in figure 9.1a, 9.1b, and 9.1c. Terms in simple harmonic motion. Amplitude is defined as the maximum magnitude of the displacement from the equilibrium position. Its unit is meter. Period is defined as the time taken for one cycle. Its unit is second. Equation T equals to 1 over F. Frequency is defined as the number of cycles in 1 second. Its unit is Hertz. 1 Hertz equals to 1 cycle per second equals to 1 per second. Equation Omega equals to 2 pi F, or F equals to omega over 2 pi. Displacement x. Uniform circular motion can be translated into linear simple harmonic motion and obtain a sinusoidal curve for displacement x against angular displacement theta graph as shown in figure 9.2. At time t equals to 0, the object is at point P, and after time t, it moves to point N. Therefore, the expression for displacement x is given by x equals to a sine theta, where theta equals to omega t. In general, the equation of displacement as a function of time in simple harmonic motion is given by x equals to a sine omega t, where x is displacement from equilibrium position, x is amplitude, omega is angular frequency, and t is time. The unit for displacement is meter. Phase. It is the time varying quantity omega t. Its unit is radian. Velocity in simple harmonic motion. From the definition of instantaneous velocity, v equals to dx over dt, and x equals to a sine omega t. Then we differentiate x. Finally, we get equation for velocity is v equals to a omega cos omega t. The equation 9.3 is an equation of velocity as a function of time in simple harmonic motion. The maximum velocity, Vmax, occur when cos omega t equals to 1. Hence, Vmax equals to A omega. The SI unit for velocity is meter per second. Relationship between velocity and displacement x. It is given by V equals to plus minus omega set A squared minus x squared. Acceleration in simple harmonic motion. From the definition of instantaneous acceleration, A equals to dv over dt and V equals to A omega cos omega t. Then we differentiate V. Finally, we get equation for acceleration is A equals to negative A omega squared sine omega t. Equation 9.6 is an equation of acceleration as a function of time in simple harmonic motion. The maximum acceleration Amax occurs when sine omega t equals to negative 1. So, Amax equals to A omega squared. The SI unit of acceleration in simple harmonic motion is meter per second squared. Relationship between acceleration and displacement x. It is given by A equals to negative omega squared x. Caution: some of the reference books use other general equation for displacement, such as x equals to A cos omega t. So, equation for velocity in terms of time becomes V equals to dx per dt equals to negative A omega sine omega t, and equation for acceleration in terms of time becomes A equals to dv over dt equals to negative A omega squared cos omega t. Energy in simple harmonic motion. Potential energy. Consider the oscillation of a spring such as a simple harmonic motion. Hence, the potential energy for the spring is given by U equals to half kx squared and k equals to m omega squared. So, U equals to half m omega squared x squared. The potential energy in terms of time is given by U equals to half m omega squared A squared sine squared omega t plus phi. Kinetic energy K. The kinetic energy of the object in simple harmonic motion is given by K equals to half mv squared and V equals to omega set A squared minus x squared and K equals to half m omega squared A squared minus x squared. The kinetic energy in terms of time t is given by K equals to half m omega squared A squared cos squared omega t. Total energy E. The total energy of a body in simple harmonic motion is the sum of kinetic energy K and its potential energy U, where E equals to K plus U. From the principle of conservation of energy, this total energy is always constant in a closed system. So, E equals to K plus U equals to constant. So, equation of total energy is given by E equals to half m omega squared A squared or E equals to half Ka squared. Graph of displacement against time. From the general equation of displacement as a function of time in simple harmonic motion, x equals to A sine omega t. So, graph for displacement against time shown in figure 9.3. Here is a period. Here is amplitude or equals to x max. Graph of velocity against time. From the general equation of velocity as a function of time in simple harmonic motion, v equals to a omega cos omega t, the velocity time graph is shown in figure 9.4. A omega represent v maximum. Graph of acceleration against time. From the general equation of acceleration as a function of time in simple harmonic motion, a equals to negative a omega squared sine omega t. The acceleration time graph is shown in figure 9.5. A omega squared represent a maximum. Graph of energy against displacement. Straight line graph represent total energy. Brown graph represent potential energy. And blue graph represent kinetic energy. Period for single spring oscillation, T is given by 2 pi sed m over k, where T is period of the spring oscillation, m is mass of the object, k is spring constant or force constant. The condition for a simple pendulum execute simple harmonic motion are: the angle has to be small, must less than 10 degrees, the string has to be elastic and light, the only gravitational force and tension in the string acting on the simple pendulum. The condition for the spring's mass system execute simple harmonic motion are: the elastic limit of the spring is not exceeded when the spring is being pulled, the spring is light and obeys Hooke's law, and no air resistance and surface tension. Let's continue with multiple choice question. First question, which of the following statement regarding simple harmonic motion is true? The answer is D. Speed is maximum at equilibrium position because kinetic energy is maximum at equilibrium position. In which second question, in which group below do all the three quantities remain constant when a particle moves in simple harmonic motion? The answer is C. The total energy, amplitude, and angular frequency remain constant when a particle moves in simple harmonic motion. Third question, for a system in simple harmonic motion, which of the following is the number of cycle of vibration per unit time? The answer is C, frequency. Fourth question, which of the following statements is true about a particle that performs simple harmonic motion? The answer is C. The motion traces a circular path. Last question, which of the following statements is true about the period of oscillation of a pendulum? The answer is B.